learn one definition of non-interference. We're going back to the example, trying to figure out, can we use the model we've seen, can we use non-interference to describe what's going on here, right? So I'm going back to the heat map situation. So for non-interference, can we say that this program that's outputting this heat map of emitter-based violates non-interference?
It violates non-interference if the running data is secret. It doesn't, like, the fact that it aggregates it doesn't change the fact that it violates non-interference.
Yeah, so the non-interference I gave is very strict, right? So there are actually two different aspects we're looking at. So typically heat map is considered okay. The problem here is that the location of the heat map is also sensitive. It's not just individual data being sensitive. There are two kinds of sensitivity or two kinds of secrecy label going on here. So in this particular example, even if I allow heat map, because that's considered aggregated data, it's preserving individual person's privacy, this is still not okay because of the nature of this map, right? So now, if this is not a military map, I do want to allow heat map. It's actually fairly useful functionality to allow me to know where people are running, right? So in general, users don't mind being in part of a large set of data, de-anonymized aggregate data. This is actually very common. We see average salary, we see average height, average weight. We see the statistics of disease connected to certain things, right? So that's actually important data for research in general. So we need data like this. But our non-interference have issues with it. I cannot allow this to happen. That means my non-interference is actually too strict. So I'm going to stop with the example here. We'll address this constraint later in this lecture. Now I'm going back to, let's see. Going back to the part, all right, just do a quick summary. So we went through this. We look at the example. Most of it makes sense. The non-interference part is difficult. Also, different models require us to actually define different observations, right? So we started by saying, hey, here's the end result. The attacker can see the part of the memory that they're allowed to see. And then quickly, when we look at other examples, timing and termination become a channel, right? Also, in this definition, in this model, we haven't talked about how do we handle aggregate data. So this is collectively called declassification. You do something to the data to make it less secret. Or even in government file, something happened way in the past, the government would put a declassified stamp on the file and then release it to public. Right? That's another kind of declassification that happened fairly common. And then at the end of last lecture, we're staring at the while loop, right? The one where you kind of encode the password bit by bit or character by character. That one, now the assignment touched secret in a way, right? Somehow it happened inside a branch that, depending on secret, become the issue. Our model so far hasn't said too much about it, right? So that's where we are. So this is kind of sort of the direct limitations there. In terms of programming models, so far we've been thinking about sequential programs, right? So it's a very simple program. But then you also have program that's concurrent. You have multiple threads running. You also have other non-deterministic programs. I know some of you are working on probabilistic programs, right? So there's distribution of inputs. You can toss a coin, so on and so forth. Right? There are different modes of operation. So in the case where the program actually might have a set of inputs, you run the program, there are possible results. Maybe the simplest thing to think about is with multiple threads, you can get different interleaving, depending on scheduling. Depending on how schedule work, you will get different sequences of outputs or different results of final memory just because of the interleaving, right? So in those settings, typically this is like one of the earlier definitions of non-interference to deal with programs that have returned a set of results or have a set of possible results is this possible non-interference, talking about possibility. So basically, this is saying that if I run a program, so again, I still do, you can still think of two traces, two different inputs that differ in secret. So basically saying that if I run one, every trace in one, I should find a corresponding trace in the other run, in the other set of possible results. Right? For all exist. So that's the definition here. So the problem with this definition is that it's highly depending on the scheduler. If you have a completely non-deterministic scheduler, this is okay. The attacker actually this definition is strong enough. The means that the attacker cannot deduce what the secret might be, because everything that they see on one set of secret input, it's possible that it's matching another trace with a different set of input. Therefore, the attacker has no understanding of what the input value is. However, in general, the scheduler, it's very rarely we have a non-deterministic scheduler, right? We have priority-based scheduler, we have round-robin scheduler. These are common schedulers being implemented. So therefore, once you settle down on one scheduler, this definition actually allows something called a refinement attack. So basically, so if you look at this program, we have two threads running. So I put parallel bar together with the second program, but this is like parallel composition of two programs. So the first program basically sits for a while with the secret 1, then output 1. This L meaning that output to a public channel. The second program just output 0 right away, right? Do a shorter computation. So if I think about if my scheduler is non-deterministic, I can run this, like doing random over interleaving of any sorts. The possible result of this program is either output 1 after 0 or output 0 after 1, right? So no matter what secret is, for every trace you see 0, 1, you can see another trace 1, 0 when the secret is 0, right? So it's this program under a non-deterministic scheduler satisfy this possible for exist definition of non-interference. Yes? Any question about this? Still following this? All right, so now if you think of, now I'm actually running a realistic scheduler with round robin. Right? I do thread 1 first, then I run thread 2, then thread 1 again, thread 2, so everybody gets a chance to run. Right? This is quite common. What's the problem if I run round robin?
Yeah, it's always going to be 1, or it's always going to be 0.
If the secret 1 is always going to be 0 and 1, right? So I'm refining the result now. Now this for all exists doesn't quite work anymore, right? So the attacker can deduce some thing about the secret if the output is 0 and 1, right? So that's called refinement attack, right? So basically, when you do for all exists, you're kind of doing simulation one way, but if your refinement is pulling some traces away, suddenly this exists may not actually be found anymore. Right? So that's a common problem. Now, in this lecture, I'm not going to concurrent system or other kind of programming paradigm too much. This is just to give you an idea of there are many different definitions of non-interference. Right? There's a straightforward one. Different systems actually require you to define different non-interference depending on the observation, depending on the underlying architecture of the program, and so on. All right, any questions so far? All right, so this is like the end of the first section. I didn't quite finish yesterday, but basically what we did is we did a bit of history tracking of back then. Essentially, we're trying to get you to the point where you understand that information flow is trying to enforce a global property. We're trying to track the entire information flow end to end, versus access control tend to be local. They check step by step. It doesn't mean that access control system cannot enforce non-interference. It's just at a high level, non-interference is considered more global, stronger. So in the access control literature, if you follow companies like SegMat, at one point they introduced this access control policy called sticky policy. So basically saying that the purpose of the data, you stick the purpose with the data as the data flows through the system. This is like information flow, right? The label you give to the data in the program stay with the program. So that's also, in my view, is equivalent to information flow. Right? So we talk about non-interference. So yeah, I was saying that the reason why I put BLP at the beginning because it's a transition between access control and information flow. When multi-level security BLP were introduced, they were introduced in the context of access control, but gradually we moved into information flow security. It turns out that the policies that BLP implement actually enforce non-interference properties. Yeah, so definition, again, it's a jargon. So when we define non-interference, we typically look at two executions. So it's called the two-trace property. Your general 16 Leibniz property saying that the attacker can never open a file or the attacker cannot send over data to the network. These are called safety properties. You only need to look at one trace of the execution to decide whether this execution violates the property or not. Versus non-interference, we always talk about two traces. So there's a very nice paper published by CSF. They defined a set of properties called hyperproperties. After this paper, their whole bunch of work following hyperproperty monitoring and so on. Okay, so the last point is there are different ways to define non-interference. From four methods perspective, how to define non-interference so it actually makes sense. That's actually quite interesting. It's a very interesting aspect of us doing information flow security in this area. All right, so that was supposed to end yesterday, so now I finished this. Now I want to go talk about approaches. How do we enforce non-interference, right? So when we look at BYBLB, I kind of talked about, if you think about it in terms of access control system, they're actually enforcing it as a runtime monitor, right? When the request comes in, the system decides is it according to policy or not. Reject the request if it doesn't follow the policy. So for the property, we can also enforce the property statically. Right? The type system is one approach to enforce this statically. So basically, the nice thing about type system is that you make your policy very explicit. Right? The programmer will specify your information flow policy on data and programs. So not super consistent, but here S is secret, P is public. Sometimes we use high and low. So high means is the same as secret, low is the same as public in general. So let's say that I have letters, I have 2-point letters for secrecy. P can flow to S, or P is lower than S on the letters. So then in your type system, your foreign type, say int or bool or function, int, arrow, int, and so on. Now in the information flow type system, I make the information flow policy explicit on the types. Right? So instead of saying int, I said this is a secret int. So I mark this as int S. Or I say this is a public integer and I name it int public. Right? Sometimes people write this as superscripts up here. For PowerPoint, when I'm lazy, I just put it on the side. But you know what this actually means, right? I think somebody asked me yesterday. So this is like if you are doing any monetic types, doing any effect types. So this is actually behaves very similarly to a monad. So I'm qualifying the type based on the information flow label. Right? All right, so we can imagine that what I want to enforce in the type system is that for secret data, somehow it shouldn't be depending on public data, right? So I'm doing a dependency analysis in my type system in some way. So basically, type checker look at the programs effectively and decide, yes, this is okay. If it's well typed, I'm actually supposed to enforce non-interference. Or in a thorough type error, I'm going to say the program might leak information. Because the static analysis, typically they're over approximation, they're conservative. So when the type checker said, oh, this might be a problem, doesn't mean in reality there's a problem. It's just the type checker will conservatively reject the program so that it definitely won't leak information. So the runtime monitoring part, like VBA, is kind of like that. Don't worry about what's in the state now, but basically these represent the state the program runs in, and then the third monitor seeing every step of the program running, then decide, yes, this is okay, to go to the next state, or they abort, they stop, to say, no, this is not okay. Another option is they would rewrite the program slightly, not the program. When the program decided to do something, the monitor decided, no, you can't do this. But instead of terminating the program, the monitor might decide to do something else or ignore the current instruction and go to the next one. The monitor have a few things they can do in addition to just allow or deny. There are other things that the monitor can do. So those are two main approaches. So today, let's see. Yeah, today I think I will cover the type checking thing. I don't think I'll have time to go into the monitor side, so tomorrow I will go into the monitor side, and if I have time, I actually want to discuss a work that we have where we use gradual typing to connect the typing with the monitor world together. Okay, so that's super high level, so let's jump into information flow types. So I use some slides, and then I'll start using the board, so let's see how far we can go. So we're going to have a very simple language. There are no hierarchical functions, there are no hierarchical for. Think of your C without pointer arithmetic without function pointer, without struct, super basic. So here, values can be either variables or integers. If I don't use these booleans, right, you think if it's greater than 0, it's true. If not greater than 0, it's false, right? That's how I interpret if I do if branching. So these variables actually are the C kind of variables. When it's assigned to it, it's actually mutable. They're mutable variables, you can actually multiply in the store. And then for expressions, generically some binary operation, some linear operation. This can be plus, can be and or, this can be not, negation, minus, and so on. And then for commands, I have no up or skip. So this basically doesn't do anything, but might take a clock cycle. Right? And this is also instrument for me to define semantics. When I finish executing something, I'll use skip, marking the end of something. A no op. And then we have assignments, right? So this is your mutable assignments, right? When I assign this, actually what store in X on memory, in memory actually gets changed. I don't have a branching. We have while loop. So actually, in terms of doing formalism, we're just ignore loop, this while. This while is kind of expanded if. So we do mostly focus on if. Whatever type rule we use for if typically work for a while, except under termination, but we'll probably not get to termination today. Okay, so then that's your surface language. And then for runtime, we have a memory, the state, we have the store called sigma. So sigma basically maps variables to its value, right? So it's a sequence of x, y, z, whatever, and the value is stored. Now, in terms of semantics, I'll write on board later, one of the proofs, but you can imagine what the semantics might look like. So expressions is considered effectless, effect-free in the sense I don't modify memory, so I'm going to use this notation saying, hey, the value E under the sigma, let's give me a V, right? So you can imagine the evaluation is so that if it's X, I just look up, right? If it's binary operation, I just evaluate either one of them, then compute the final result, right? That's the simple semantics. And then I have command semantics. I'll write it later when we actually do proofs, but you can imagine basic skip does nothing, we do assignment and arbitrary store, so on and so forth. Okay, so the interesting part is this information flow type system, right? So I'm going to use the 2-point letters, now I'm going to use the high and low now. This is the same as P and S, just different names. So for example purposes, I say that typically you have a typing context, right? So I have to type all my variables. So in your typing context gamma, there's a list of these type mappings. So for example, I say x has int low means that x is integer, or x stores integer. This integer does not contain a secret. Anybody can see that. And then y is it has type int hide. I meant that y is variable and store a secret value. So that's an interpretation of the variables. So I have two kinds of typing. I put the expression typing on the slide. We do command typing. I either have it or I will write on board. So for expression typing, basically, I have this gamma, the map variables to its type. Now type check E. Now typically it should be tau with some L. Since I only have integer, I'm just lazy. I'm not going to write integer everywhere. And also I don't have functions, right? So I'm just going to type E as a security level, right? If I need boolean or int, this is going to be a tau with L. So here I just have L here. So this is completely straightforward. So when I do binary operation of two expressions, if the sub-expression has a security level at security level L1, L2, when I combine them, I also have to combine their labels. Right? This is a label drawing I'm going to take. That will be the resulting label for the data. But the same as if I take a paragraph from a public article, I take another piece of data from a confidential document. In the end, the combined document will be confidential. So their piece of data needs to be protected at that level. That's what I'm using it for. All right. I do have command typing. Good. I did put them on the slides. So for command typing, this is actually not the first paper in 96, the O'Connell Smith paper. They actually didn't use this thing called PC. This paper actually happened maybe 5 years later. So the idea is that when we stare at the while loop, we realize that somehow if you are, if branch 2, if you're actually operating, if the command is executing under a branch that depending on secret, we have to treat the command differently. Right? When you do typing, that means that when you type check a command, you need to know whether the command is executing, will be executed under a high or low context. Right? So this PC, I think this is actually ill named, they call it program counter. So this is really the typing for the context, not your program counter as in your assembly architecture class where this register storing where the program is at, right? But this is like the context label. It's also a label itself. Okay, so in the first paper, Smith instead actually put the PC kind of at the end. If you read that paper, I think it's actually less intuitive than this kind of typing. But if you have questions, you can ask me. I'm not going to present their system. Instead, I'll present this system that uses PC explicitly. Okay, so now where I use PC, right? So the if branches is where I'm going to use PC, right? So here, this if branch itself is being type checked under its own context label. We call it PC. Now I'm going to type check the boolean. It has some label L. So when I type check the sub command C1, C2, because now I'm under this inner branch, right? So therefore the context has to be the current context joined with whatever this branching is, right? Even if I start from low context, now if I branch on high, I'm supposed to type check the sub expressions under high context, right? This is how I keep track of whether my while loop is depending on secret or not, right? Because if I'm in a high branch, we saw that in the programs, for implicit leaks, if I do assignment to a low variable, I'm actually allowing the attacker to see a different observation, right? So the type checking for C will rule out certain assignments if the context is actually high. Right? Any question about this? This is like one of the tricks in information flow type system. When you see it, it kind of makes sense. It did take people a bit of time to actually reach to this point.
Yeah. Also, just to double check my understanding, we were saying that an if statement is impossible to build if we don't have the high-low, the correct relationships between the types above, right?
Possible to build. You can type check. You should rule out programs that behave badly if you're under a high, quote-unquote, high context. Yeah, but then the high and low is relative, right? So I'm using high as an example. So let me actually show you where this is used. I want to say this rule is slightly wrong, but right for the current purposes, which is not wrong for now, we'll talk about why this is wrong later on. So in assignments, right? So this is actually, if these two rules combined, is where we're trying to rule out implicit flows, like the one if high, then x equals 0, else x equals 1. So we're trying to draw that program. So here when we do assignment, this kind of makes sense, right? I'm trying to update x with e. Their label have to match, right? So this is fairly strict, but I'm going to stipulate that now. Later I'll make it slightly less strict. So basically, if you have low variable, you can only assign to low. If you have high variable, you can only assign to high. Right? This seems fine. This enforces that I'm not going to put secret into a low variable here. And this one is, I'm trying to rule out the implicit flow. This is saying that, well, I need to know where I'm doing the assignment. Right, so if my variable is low, if I'm actually under a high context, this condition won't hold. So what I need to do is make sure when I do assignment, my context has to be lower or equal to my variable level, right? So sometimes people call this variable is protected at this level. And now you want to make sure that the PC you're operating under has to be lower or equal to the level you're protecting the variable itself, right? So in the implicit flow example, if you have branching on high, the PC will be high, and you're assigning to a low variable, this is low, this relation doesn't hold. That's how the type system rule out implicit flows. The same for while loop. That's why it's for while loop here. It's very, very similar. Yeah?
Why isn't that side condition about PC is less than L, it's not present in the rule for if then else, and I would expect it to be there somehow, somewhere, like maybe that like C1 is the level for C1 is like.
Yeah. So basically that's a OPLSS system. So here so you can somehow assign a level for the operation in C, assign commands a level, then you check it here. You can do that. So here I'm doing latent check. So I'm only doing, I don't know what C is doing, so instead I know what C is operating under. And then when I get to the place inside C where the assignment happened, because I know what context I'm operating under, I can rule out program here. So there is an equivalent system where you can give C a label, checking what C is assigning to, right? If I assign to low variable, I say, okay, C has label L. The command has label L. And then when I do while loop here, or if branches, I need to make sure my branching cannot be, this condition holds for that. Yeah, but here I'm kind of save it for later.
Yeah. So from like an implementation perspective, like PC is like trash, and the like a conclusion of the second rule. How would you refer what PC is? Because you can't look at E or X.
Oh, so the direction of this type checking. So this is the gamma and PC is given. You always start checking your program in a low context. When you run your program, there's no secret yet, right? You just start running your program. So when you start type checking your program, you always start in low. And then when you recursively call the sub expression, sub commands, that's where you compute, right? So every time I'm here, this is always known. Because when I start, this is known. The first program, the high-level program is always low. As I'm recursing deeper, this is known, right? It's always known. Yeah, if you do logic program, you think of input output, this is always input. We don't need output here. Yeah, if you're trying to inference, that's a slightly different mode. Yeah.
Can I ask for the context in this type system? Are there sequences of?
Yeah, so the gamma actually has that kind of works. This is kind of example gamma. Your gamma, this standard gamma is just either empty or gamma X type S. This S will be of this type. But now I got rid of int, so you can think of this as L. Yeah, just a set of bindings. Yeah.
So for the assignment rule, remind me why E and X has to have the same security label.
It's a good question, why, right? So it seems like there's safe things to do. What's safe to do?
It seems like I can go from something that is not secret and then write it to something.
Yeah. So basically,
violates integrity, right?
Yeah, I can take some public article, mark it secret. So what, right? So therefore, there is subtyping, right? So yes. So yes. So if I type check E, sorry, I think that this typo here should be both E. No, I think the copy paste problem. Yeah, if I type E at L1, I can also type E at a higher level. I'm just protecting them more. There's no harm in this, right? But now I actually have a problem. Combine this subtyping with this assignment rule, now I actually have a problem. I'm going to take a break and you guys can tell me what's the problem there. Talk to your neighbor if you're not sure. Yeah, feel free to discuss. Yeah, so this rule, this place become weird, right? So now I can take a low variable. Now I can also type it high. Now I can assign secret to x even though x is low, right? That's a problem. So these are left values. We actually have to treat them very specially. This is wrong, right? So I don't have pointers. So I will not actually have ref rules probably at the end of this lecture. So here, typically for this simple system, we don't do this. I have to actually do this. I just directly look up x here. So, and to make sure this left value, I don't subtyping there. It's okay for the right value to be subtyped, but left value, no, we can't. Right? I mark this variable as being low. I cannot use subtyping rule to say, hey, now actually x can also be high. Right? That's the problem here. We only need expression. For command, we actually don't need, because for command, because first of all, command have no label. Only command only have a context. So yes, there's things to play with context. So you can do some weakening on the context, but we don't need it because it's admissible. You can prove that's true rather than writing rule about it. Yeah. We'll get to it. Yeah.
Sorry, to make sure I understood, the problem with the combination of these rules is that it lets you assign the secrets to a public variable because you just say, well, the public variable is a subtype of pi,
Yeah.
so let's just assign a secret
Yeah.
to it.
That's wrong reasoning, right? Because we're talking about address, not the value itself.
Okay.
Yeah. So when you deal with refs, you have to be super careful. So that's another sticking point in information flow type system. So if you design information flow type system, there are just this many things you have to watch out for. Typically, branches, loops, loop conditions, and assignments. These are places you have to watch out for. Yeah. All right. Any other questions before I move on? Okay. So now I'm going to try to do some non-difference proofs. Let's see how this is going to go. So I'm going to completely get rid of this. Do I need to write language? The language is so simple. Hopefully, maybe I don't need to write language because when we define stuff, the construct will be there explicitly. So I'm trying to. Let's see. All right. Okay, how does this work? I haven't really kind of whiteboard for a while. Okay, so let's start with E. So I want to define non-reference. Obviously, E is part of C. Eventually, I'll get to C, because in the end, the program is a command, but it calls into the execution of E. If I want to specify a non-interference theorem about E, what should I be writing about? So the E I have is, they're well typed, right? So I know that